In the last video, we talked about small angle approximation, and we found that these equations were valid for the angle as a function of time, the angular velocity as a function of time, and the angular acceleration as a function of time. And I just wanted to mention, this begs the question, what if the angle is not small? What do you do? I'm just going to show you what I would do. And I'm going to go to a screen share. So I haven't worked this all out for you because I thought this might be something we someday do in lab, but you could imagine you make a simulation. And so that is clearly a large angle oscillation. So you might be wondering, what's under the hood? How did I figure this all out? How did I figure out all these parameters like the velocity, which is required to get the AC? So let's go ahead and look in here under the hood. So there's a bunch of constants. I think I like that. Thanks, Alan. You're the man. All right. Alan helped me do a lot of the cosmetic. Let's just get to the guts of the code. All right. So there's going to be some while loop in here, and we're going to initialize this. And so what I do is, just like we did in our problem on the board, we get the torque. And then from that, I can get the amount that the angular momentum changes. Plus equals here means change this. So this is essentially the equation L dl dt, excuse me, is equal to torque. Torque changes something's angular momentum. So this is angular momentum. So you use torque to change the angular momentum. And I can see I'm going to run into trouble here. So I'm going to change the marker color. Okay, there we go. All right. Alpha, this equation is just sum of torques equals I alpha. And notice the computer defaults to assuming a positive value, positive direction here, but we can get a negative number for it if the torque is negative, just like our derivation on the board. Omega, that's just L equals I omega. And I believe omega, and so notice torque comes from a cross product. It's a vector, so this had better be a vector too. So I've chosen to use vectors for angular momentum and torque and alpha. And you might want to discuss with your teachers, this is only valid when we have rotation in a single plane. So you can't treat the angular acceleration or the angle as a vector if we're rotating in 3D space. That's a different problem. Anyways, okay, the change in angle, I clipped off the z component. If you recall, we were assuming this was x, this was y, and out of the page was the z direction. We kind of talked about this. So again, you line up your thumb with the z-axis and your fingers curl around the z-axis. So the amount that the angle changes as you go around the z-axis, this equation is just omega subscript z equals d theta around the z-axis dt. So I rearranged this equation to get that equation. And then from there, there's a bunch of cosmetic stuff. Obviously, I didn't get the period in here, but I think you could figure that out. You just run a timer on the clock. But notice how I actually rotated things here. So in Python, you specify the change in the angle. So I'm going to change the angle each time step by this much about the pivot's position. And the axis, this is going from the pivot to the point where the ball is located or whatever. So this would work for a physical pendulum as well, because, maybe I didn't, MOI means moment of inertia. So I know I'm just sketching this out. My goal is not to do this for you. Maybe you could do this in lab someday. But I did want to point out, the short version is, If you have small angle oscillations, usually we use these exact or these approximate analytic solutions. And if you have large angle oscillations, you probably need to simulate it with a code or do some kind of numerical technique. That's enough.